Alright, so this time the first thing I need to do is define the function a of x. And then we're going to define our approximate solution equal to and I'm going to go ahead and use Mathematica's ability to generate a sum for me. I want this to be actually 0. Okay. All right. So everybody okay with what I did there? So I actually used Mathematica to generate the algebraic polynomial. Okay. Let's start with, we'll just start with a linear polynomial. So that C0 is a constant and C1 is a constant. And that's what, that's what we want to find. So now we know the functional is all right. So there's the integral evaluated, and we want to minimize that. Now we have two coefficients. I'm sorry, see, I'm already messing up. we never satisfied the boundary conditions. Okay, so this is actually what I wanted to show you how Mathematica can help us do this. So the first thing, we can just allow Mathematica, so we want u at 0 to be 0, so that implies that C0 has to be equal to 0. So if we tell Mathematica to solve u at 0 equal 0 for C0, then there we have the solution, okay? And we can then define u of h equal to what it was before, but evaluated with C0. So that slash dot right here means I'm going to evaluate the solution sol1. So it's going to plug in this number into this and give me a new function. Okay. So there's what I get. Okay. It's not too difficult when there's only one term, but we'll add some terms here in a minute. So now if we evaluate the integral, we have that, which we can then, if we take the derivative of it with respect to C1, set that equal to 0, and we solve for C1. If you notice, I know that we know what the solution is, and it's not right. So I messed up on the functional. There should be a 2 right there. If I put that in and do that, and then finally the last step is to reevaluate this with the correct term. Okay, that's not right either. The dangers of doing this on the fly. Does anybody see where I made a mistake? Ah. Yeah. No, but that should be okay. Oh, I know. I probably let's reevaluate everything. No, I didn't think I had reevaluated that integral. So what I did was I hit Control A or Command A on a Mac, and see I'd highlighted all of these things over here. Then I just Shift Enter and it evaluates everything. This is embarrassing.
That dx light input 29. When I was working on it, it would give me like a bar after the d. Is that what that is, or is that just the screen? That just says dx.
It's just the screen. There's a bar there.
Okay.
It's zeroed. Ah, thank you. I'm doing everything analytically. I need to continue with that, but there it goes. Yeah. So then, yeah. So then if I evaluate this at exit equal to L and simplify it, we get the right answer. Thanks. That's the problem. All right. So let's look at something a little more interesting. Let's change this to 1 minus x over 2L. All right. And in order to know if we're going to actually solve this analytically as well using Mathematica's dsolve, because you won't know how well we did because the functions look so funny at the end. Anyway, so the equation here is, I'm going to actually solve this. Subject to the boundary condition u0 equals 0 and e ax u prime L equals p. All right, and it doesn't like my E. All right. So, everybody okay with that? So I'm just using now, but I haven't reevaluated A. So when I reevaluate A, this is going to get much uglier. It's going to become that 2 log whatever. Okay. So let's do that. So here is the approximate solution, approximated with one term, and here is the analytic solution. Okay, but we don't, we can't simplify. We don't know what those logs 2L minus X are. So if we plug in some numbers, it'll help us. So I can plug in numbers. First thing I'm going to say, I'm going to evaluate X at L, and I'm just going to plug in ones for everything. So L equal to 1, P equal to 1. What else is in there? AO equal to 1. EY equal to 1. And we need to evaluate that numerically. So that's what we get. Okay? So if we tack on all this to here. Okay, so using one term approximation, that's what we get. But this is the true answer. Okay, so that's not terrible for one term, but let's see if we can do better. So if I add a term here, that becomes that, okay? I need to make it admissible, which we still do there. So now, after substituting in C0 equals 0, the polynomial looks like this, okay? Now we have a new quadratic function that we want to minimize. It looks like this, okay? But now we have we need to do this, we need to minimize it with respect to both C1 and C2. So I'm going to take the derivative of that function with respect to C2, set that equal to 0, and then solve this for both C1 and C2. And I get that, and then if I plug it in there, I get some numbers. 1.3846. We're looking for 1.3862. So we got a little better. All right. Let's go back up here. Let's add another term. Okay. Now the polynomial looks like that. The integration functional looks like that. We have to minimize with respect to the C3 term now as well. So we'll add that in. Solve for all three. You get that. It's pretty good for an approximation.